Hi, everyone. I'm Hamid. How are you all doing? I hope we're doing well. Can I ask a question? Can you raise your hands if you've ever seen nuclear fusion? You should all be raising your hands. The sun is nuclear fusion. It's, it's a nigh incomprehensible amount of power that scientists have been attempting to replicate on Earth for about 70 years. It's considered the holy grail of the energy crisis. And for the last 70 years, the running joke has always been, how far away is nuclear fusion? It's about 30 years away. However, in December of 2022, a team at the Lawrence Livermore National Labs was able to pull it off. From that team comes our speaker today. She's also a UC Berkeley alumni, having completed her master's and PhD here.
Yay, go Bears!
And after publishing her paper, she didn't stop there. She's gone on to help co-found Inertia, a company that aims to advance nuclear fusion technology as well as commercialize it. So please put your hands together to welcome Dr. Annie Kritcher.
So before we get going, this might be a little bit of a different format, but I decided to share a few slides since what I'm talking about can be a little confusing. And it's always nice to have some eye candy to think about while we're having these discussions. So last time I came here, I was very excited to come back, and thank you very much for the invitation. I spoke about the fusion breakthrough, which is we finally got more energy out from fusion than energy into the experiment, and it's still the only approach that's done this so far in a controlled way. And I was asked by somebody in the audience, why haven't you left the national labs already to go found a company and commercialize on this result? And so I'm really happy to talk about Inertia today, which is taking that scientific achievement from the lab to commercialization. And here we do a lot of prep, decades work of preparation, and also years work leading up to a specific experiment at the National Ignition Facility, only 50 miles east here in the middle of nowhere, Livermore, California. But here's a fly-through of the facility of what happens when you press go on a shot day, and a rendering of what happened on the historic ignition experiment. And so I'll be voicing over this, speaking very rapidly, hopefully not too rapidly, and so happy to also replay a few times. So our control room is modeled after NASA. We have all the different components of the system set up and ready to go. We hit go. We have 192 laser beams. Half of them come in through the bottom of a 10-meter diameter chamber. Half of them come in through the top. We change the color at the last minute. All those laser beams go into a tiny little target about the size of a pencil eraser. That creates a 3 million degree X-ray oven inside of this little hot can. We have a BB-sized capsule that sits in the center of that can. The capsule contains deuterium and tritium, which fuse together and give us our energy. And the way that happens is we heat up the outside of that little capsule, it explodes, and just like a rocket, that squeezes and compresses down the DT fuel to star-like conditions. And then all the fusion comes out in a very, very brief moment in time, that flash. That's when we got more fusion energy out than laser energy into the target. And that was a historic breakthrough. Because it's so hard to create these star-like conditions. Usually you spend more energy to create these conditions than what you actually get out in fusion. However, even though that experiment proved something really, really important, that the physics is working and the smallest scale of driver that we need to get to these conditions, it didn't solve energy. And that's because even though we got more fusion energy out of the target than we put into the target, we didn't get more out than what we pulled from the grid, so wall plug efficiency. And that's because at the lab, it was never designed to be efficient to put energy onto the grid. It's a science experiment. And so what we're doing is at Inertia is developing the key technologies that are required to take this from the laboratory to commercialization. That includes increasing the wall plug efficiency, so what we draw from the grid to our target. And then another key aspect is increasing the entire size of the system because you get more fusion energy out non-linearly, exponentially, as you make your system bigger. We need to be able to do this continuously over and over and over again. So that was one shot, one experiment pulsed. We don't just hold and confine these conditions continuously. It's pulsed, sort of like your car engine, 600 RPM. That's exactly how fast we need to do this, 10 times a second. And since we're doing it at 10 times a second, we have to do this 1,000,000 times a day, and that means making mass-produced targets cheap enough, of high enough quality, so we can still get them to ignite and burn. And so those are the key things that Inertia, which is a commercial fusion company, is focusing on. The first one is making the lasers more efficient. So we're going from flash lamp pumped solid-state material to diode pumped. And the key takeaway here is by doing this simple transition, which our society has done many times, it's like going from vacuum tubes to transistors. We can increase the efficiency by more than 20 times, and we can increase our shot rate from 1 time per day to 10 times a second, or actually even faster than that. The next thing that I mentioned is we need to make the entire system bigger. So to get much, much more fusion energy out, enough that this makes sense, we need to increase the size of our system by a factor of 5. So even though we have the biggest laser in the world in Livermore, California, we need to make it 5 times bigger. But because we have these tiny little diode stacks now driving our laser system, the form factor of the building doesn't go up by a factor of 5, and that's really important. By doing that, increasing the system by 5 times, we can increase the fusion energy output by 75 times, and this gives us an overall increase in our wall plug efficiency of more than 200 times versus the NIF experiment. And that's how we get efficient enough conditions to have this make sense. Of course, and do it over and over and over again. And so when you're doing that over and over and over again, we need to shoot 1,000,000 targets a day. We need them to be affordable. We need them to be high enough quality because a little perturbation can jet material into your implosion, can hurt your star, cause it to be a dud. And so we are doing, this is another key research area for Inertia. We are using standard processes for all of the target components for mass manufacture, processes that are used in the semiconductor industry, so a lot of piggybacking off of the recent successes and booms in that industry, just tailoring it to our specific geometry. So instead of on flats, we're doing it on spheres. So we're really trying to piggyback and learn from what's being done in industry currently. And to put this in perspective, we need to make each target $1, and the materials that go into each target are less than 3 cents. So most of the work is in the process, development, and machinery, and so that's what we're focusing on at Inertia. And one target, one shot that is done over and over and over again can power a home for about 2 to 3 days. So putting all of this together, see if we can get this video to play. It's a cool video. Okay. Putting all of these components together, we go from the NIF experiment that was not wall plug efficient to something that is a feasible gigawatt electric class power plant, powering 1 to 2 million homes. And really the focus here is that we've demonstrated in the laboratory we can make a little miniature star 1 time, actually more than 1 time, we've repeated it. But now at Inertia, we're figuring out how to do this over and over and over again, on demand, reliably, and at cost, so that we can have star power for life. And that's our slogan there at Inertia. So with that, that was the brief introduction that I had, and we can move on to the discussion.
Yeah, that is fantastic. When you see that building at the beginning of the city, like how big is that building?
It's going to be smaller than our current NIF laser facility, which is the size of 3 football fields. This will be more like 1 or 2. We're still getting the exact details there.
So basically about 3 times as large as the stadium.
Yes.
Does that sound right?
Yeah, that's about right.
And I mean, it's pretty like mind-blowing. I just don't know anybody who creates stardust, basically, in a way. I mean, maybe, I don't know. Are there byproducts from doing this? I know this is
We
not our
completely
questions.
obliterate the target. We vaporize the target. It doesn't create any long-lived radioactive waste. So the fuel components are deuterium and tritium. They're forms of hydrogen. They make helium and a neutron and a lot of energy. But the target, the can, is made up of lead, and that is something that is recycled and refurbished, not just stored as waste.
Yeah.
So that's reusable, and it's the amount that we use in a given year is storable on site on the facility.
So I'm not sure that maybe people in the audience understood this, but I'm not sure I ever understood. So it sounds so great, but what is that going to mean for us and for our climate? What does it do for us?
Yeah, so the reason that fusion energy is the holy grail of energy is because it has no long-lived radioactive waste, no carbon emissions, it has high base load, so it's continuous, dependable. So unlike other clean energy sources, wind, solar, it doesn't rely on the weather or those conditions. So it's more reliable energy. It can help us power our data centers. So everyone here that loves AI, and from the last talk last week, it can enable that, because they need very high base load and very high energy demands and power demands. And so it could revolutionize. I mean, I always feel a little bit like I'm bragging when I talk about it that way, but that's why I joined the lab, and that's why I'm into fusion energy. I think it could revolutionize humanity.
Yeah, just in case you all were thinking that this might not impact you, if this can be put into practice, it could revolutionize humanity, which means all of us. And so I don't know that any of us think about fusion and star power every day, but it makes me feel a little bit better that there was a time in your life when you started off as a student, even though it was at Michigan. Just like
same colors, though.
all of us, yes, yeah. And same quarterback. Oh, not anymore.
Burn.
No, is that true? No. Never mind. Yes, same colors. But when you were a real person like all of us, what were you like when you were at Michigan? What were you studying?
Yeah, ask my husband. I'm still a real person. Yeah. Maybe too much. At Michigan, I also studied nuclear engineering. So I always had a love for math and science. And when you're from Michigan, everybody's like an engineer. Nobody's really a physicist. So. Went to Michigan for engineering, thought nuclear was cool, wanted to get out of Michigan, so I have that going for me as well. Wanted to come out to California, so I came to Berkeley for grad school, also nuclear engineering.
How, with Carl Van Bieber?
Yeah, he was there, yep.
And now...
He wasn't there when I was there, he's there now, sorry, I'm that old.
Was there a nuclear reactor there here when you were here?
It was already decommissioned, but Ed Morris, who ran the nuclear reactor here, was my thesis advisor.
Wow. Where was it?
It's in the Echeverry.
In the bottom
in
there?
The basement of Echeverry.
Does anybody still study in Echeverry? Are there still signs there? Does anybody see those?
I haven't been down there in a while, but...
Aren't there like the yellow and black signs?
Yeah, I purposefully didn't go down to that basement very much. Don't tell Ed I said that. So he was my thesis advisor, but I did all my research actually at Lawrence Livermore National Laboratory, at the Jupiter laser facility out there. So I started out doing laser plasma experiments in grad school, but almost 100% time out at the lab.
How did you, was it the nuclear engineering program that pulled you out to the lab? What was it about? How did you make that happen to be at the lab?
Yeah, I basically stalked the NIF, the National Ignition Facility. So I came out to the lab as a summer student first. And I just fell in love with the project. I just thought it was amazing. I really wanted a big science project to work on that I could work on for decades, which obviously is possible to do in fusion.
What was the project? When you started, do you remember how it was described?
Yeah, it was, I started in nuclear physics at the lab, and then people were gearing up to build the facility and do experiments, because I came out in 2004 to the lab. And it was just all really new. People had been waiting for this for decades, finally getting ready to put the facility together and do experiments. And so it was just described as an awesome thing for humanity, both for energy back at the time, was also for stockpile stewardship, and basic science, laboratory astrophysics.
And does the Department of Energy fund a large part of it? I mean, it is government funded. I don't know if it's only government funded.
Yeah, it's only government funded, and it's the NNSA portion of the Department of Energy. So currently it's the Stockpile Stewardship Program that funds the NIF. So we create these miniature stars in the laboratory to help test our modeling and capabilities in the absence of underground nuclear testing.
When you say you're creating a miniature star, it's that energy. That's what it is. The energy, the concentrated energy. It's
actually a star-like conditions. The materials and it's a slightly different fusion process, but really light elements getting to actually more extreme conditions, 5 times hotter than the center of the sun and 2 times higher pressure. So really creating a miniature glowing emitting star that emits neutrons. It's about half the width of a human hair. So they're tiny, but they're very powerful.
When you're in there, there's that big laser.
Laser.
How big is that laser?
It's the whole building is 3 football fields.
Oh, that's what. Okay.
And that's because those beam lines you saw, they're pretty long so that you can amplify the energy up. The new compact geometry we're looking at lets us go bigger, more energy without having to significantly increase the building size. But then when the lasers enter into the target, they're hundreds of microns, 600 microns across.
So a few years ago was when the first successful experiment was done, and you were on that team.
Yes.
How many people are on a team like that, and what was that day like?
It's the way that our teams are structured. There's so many people that contribute in different ways and over decades. So people that run the facility, we have experimentalists that set up the diagnostics will run on a shot. We have our target fabrication team that makes the targets. And this is across the entire United States. So thousands of people over decades. And then when you have a certain campaign, a campaign where you do a set of 5, 6, 10 shots to test a new idea or to test a new design, that's usually a handful of people that pull from these interdisciplinary areas.
Yeah.
So you have like a physics designer who decides how the experiment's going to come together. You have an experimentalist, you have a target fab person, a laser person, and those teams are more like 6 to 10 people.
And are those all people from academia or like mixed?
Yeah, so most of the physicists that we work with at the lab have PhDs from that they've come from academia, or we interact with academia as well. I think of academia as true professors, people at the universities, people like yourself. But yes, most of the people we work with have PhDs. In target fab and laser land, a lot of masters and bachelors.
So on that day, and I don't actually remember what day, I thought it was in the fall, but when was that first successful experiment done?
It was actually December 4th. December 4th is when the experiment started, and then it actually occurred on December 5th, 2022, so in the middle of the night.
Oh, were you there?
No, so this was coming off of COVID. We used to all go there and sit in the facility and wait for the shot to happen. Coming off of COVID, they really restricted it to just the people running the facilities. So like the physicists sort of set up the shot a week prior. And then on call during the shot day would be the lead experimentalist. He texted me. I tried to stay awake for the shot. It kept getting delayed, and then finally fell asleep, woke up at something like 3 a.m., looked at my phone, and he said, "I think we got ignition." And I said, "Awesome, I'm coming in."
Such a NASA thing. I think we have ignition.
Right, yeah. You might want to check the shot data. I think we got ignition, but...
So you proved this hypothesis that you were trying to prove, really for decades.
Yes.
That's pretty incredible.
It was a very exciting day.
What did you do to celebrate?
Went to work.
That's right. There you go. Those scientists, so much fun. I am wondering over the decades how things, like with the success, how you all keep yourselves, we were going to talk about this in a second. Let me take a step back. Chung, do you mind sharing? There's a slide that some students answered on what keeps them motivated. Yeah, well, there's a lot of different things. You were curious to know with what kept people motivated. I'm curious to know with what kept you motivated over all these years when you didn't know if this hypothesis was going to work. But let's take a look at this. I like family keeps people motivated, myself.
Yeah.
That's a hard one. Good for you. Progress. I like the honesty, depressed. Stable, financial, extraordinary, interesting. How would you have answered this question on what keeps you motivated when you were in school, when you're here at Cal, versus how you might answer it now?
Now, this is such a great question, too, because it can change day to day, right? Like some days family motivates you, some days your team members motivate you. I think for me, it's just like that there was no plan B. Like if this didn't work, my career would be a failure.
Really?
Even though that's not true, because it's science, we want to learn, and even if you don't have the experiments work out, that's a success as well. But for me personally, that's not how I felt. I felt like I have to do this or bust. And I think part of that was like coming out to the NIF in 2004, devoting my career to it, and really just, you know, I don't know, I'm just very driven.
What happened? I mean, you must have had busts along the way.
Oh, yeah.
What happens when there's a bust?
Yeah, it's so a lot of failed shots. And actually, even after the ignition result, trying to test new things, trying to make it even better. And we did end up making it better. A lot of failed shots, even in between those successes. It's, you get down, but then you get up fast. And part of that's your teammates coming together. And it's really about like, okay, it didn't work. Let's get over it. Let's figure out why. So shifting from, you know, feeling bad about it, depressed, to thinking there is a scientific reason this didn't work. And if I can figure out what that reason is, I can figure out how to make it work.
Are there anything, specific examples you can share with us? You know, there's that old story from NASA when they were trying to figure out what was the problem with, I can't remember which launch that didn't succeed. They're trying to figure it out. But how do you figure it out when you're dealing in this very small, I don't know, small
Teeny,
sizes?
tiny,
Yeah.
right. Well, luckily we have amazing diagnostics. We can look at exactly how the fuel is coming together. We have neutron pictures, so the energy coming out. We actually take miniature pictures of that, X-ray pictures. Lot of diagnostic information. And that coupled together with these really detailed simulations that we run on the supercomputers. So you start with a list of hypotheses, like based on everything that you know and the initial data, what could it possibly be? And then you sort of go down the list one by one, trying to rule out the hypotheses based on the data that comes in and the simulations that you try to match to the data.
It just seems like, I mean, it's amazing to me you don't wear glasses, for example. I mean, it just seems like a lot of looking at data and trying to understand stuff.
I have contacts.
Oh, there you go. All right, fine. Then I feel a little bit better. What's interesting is that in the last couple of years, you did shift from like, we're doing this technology and others are trying to commercialize it, to now doing what maybe I feel probably more comfortable asking you about, and that's starting a company. What was the impetus? Or like, what started the inertia? What started that rolling?
Yeah, you know, that's a great question. There was a few different things. I really wanted to rule out one of the key physics risks that I saw was still there. So once you ignite the central plasma, then you want to burn up as much of the fuel as you can, and that's really how you get your yield out. We had some question about, could we continue to burn the fuel, or was there something limiting us there? And so continuing to make that better and show that we could do that. So physics results was one of it, one of the things. The other big thing was meeting my co-founder, Jeff Lawson. So, you know, I'm a scientist. I can work day and night and forever to make something work, but I don't know how to start a company. I don't know how to do all that. And actually, it's not something that I prefer to do. So I was giving a fusion talk at a conference where Jeff was there, and he got really excited, and he was just coming off of a company that he founded, Twilio.
You've heard of Twilio?
Yeah. I don't know. I hadn't when I met him, so I wouldn't.
Oh, really?
Yeah. Who are you? No. But he was smart, though. He was an engineer from Michigan also. He did a lot of research. Actually, we spoke to each other about the physics for almost, several months, almost an entire year. Every Wednesday, we had a physics discussion.
And I would teach him. Is he also a physician? I mean, not a physician,
he's
sorry,
a
physics major.
A computer scientist. Yeah, so computer scientist. But he got a hold of a few laser books, which, and I was really impressed with his questions. And then over time, I was convincing him about the physics. He was convincing me about starting a company and that we could actually make this work. And he had all these ideas for financing and building a massive facility like the one you saw. So I think over time it was really about forming that key partnership, like de-risking some of the physics, forming these really important partnerships, and then starting to grow an amazing team. And then lastly, these contracts that we just announced with the lab, with Lawrence Livermore National Laboratory. So
what contract?
I didn't want to go off and start a company like from scratch, from zero, because I know how much effort it takes, decades, to build not just the resources and the tools, but the people and the expertise. You can't just go in a company and recreate everything that's done at the lab. Companies aren't that well funded. And so we actually, before we announced Inertia, developed these 3 massive contracts with the lab to do laser science development, target fabrication development, and also to be able to do the same design simulations that we use to design the NIF ignition experiment.
So you have 2 hats.
Yes, I do.
Your lab hat?
Yes.
And then this outside company hat.
Correct. Yeah, I'm continuing to work at the lab in my role there at the National Ignition Facility, as well as co-founding Inertia. And the reason that I'm allowed to do this is because of the CHIPS and Science Act, which is really set forth to help better tech transfer from the labs to industry, and help the knowledge really flow out to industry. And so the lab, through Kim Boudille's really visionary push to try to get this out the door, is letting me do both. And I think that's really helping accelerate the technology in both areas. And since we're piggybacking with, we're building off of what's been done at the lab, me being at the lab, continuing to drive that as well is really important.
It is like, so what is, when you're thinking about it, I mean, you've been at the lab for such a long time. What is it about working with Inertia that's fun for you?
It's, the pace. I think the pace that we can move at and the optimism, it's just really exciting. So like, you go and, I don't want to say anything bad about the lab, but, people can forget about what they're working on is so cool. You sort of get into your mode. You've been there for decades. You go to Inertia and it's a whole new mindset. Everyone's excited every single day. We're building things very, very rapidly. We already have a lab in a couple of months.
I mean,
no training. No training yet.
When we spoke, you said other companies were commercializing the technology. That was like 2 years ago. Where are you versus these other companies who've had this head start?
So most of the other companies that exist out there are trying to reach the same plasma conditions in the end to make the same star, but they're doing it in different ways, not the same way that we did it here. And that's because of a couple of key technology improvements that needed to happen to take this to commercialization. And that is what we're doing, which is distinctly different from other companies. So really driving it with this X-ray environment, so this X-ray driven environment, and diode pump solid state lasers. So a specific laser type that's been researched for many decades, bringing that to high TRL, and then using the same physics approach to get to those plasma conditions.
I mean, it really is fascinating what all is happening. I mean, here you are creating star, but you also have your own star power, so to speak. I always get such a kick out of you being named Time's 100 Most Influential People and what that involved. But I mean, you're doing stuff to totally change humanity. And has anybody ever heard of Time's 100 Most Influential list or read that? I mean, there's some really interesting and different people in there, but I wouldn't say that they're changing humanity. But I'm wondering, just for giggles, if you can tell us about getting invited, I think it's to a gala, like what happened?
Yeah, I was in shock because I had never, they're like, they gave me 10 minutes warning. Oh, we want you to talk to a Times reporter. And then during that interview, they told me about this Times 100 and I'd be going off to a gala in a week with celebrities. Get to the gala and let's see, I met Katie Couric, that was cool. The founder of Airbnb. I mean, just the list goes on. Ali Wong, we took a photo together. It was really surreal because I never thought that when I went into science, I would, take that turn. And I'm really excited to see that they are sensationalizing science now. So they're not just that one conference, but I've been to several like this now, where they're bringing together celebrities and scientists. They're really trying to make it more appealing to go into science. So I was just at the Mars conference a couple of weeks ago, the Bezos conference, where they brought together celebrities and scientists as well.
Who was that? I don't know.
I think I am allowed to say, but I hung out with Will.i.am quite a bit. That was cool.
That is pretty cool.
Yeah, that was cool.
he seems like someone similar to Jeff who'd be really interested in the science and ask you about it. What did you all talk about?
Yeah, and in fact, he was there because he was debuting his new motorcycle that he was developing and designing. So,
is it an EV motorcycle?
Yeah, it is.
Yeah.
So, yeah, and it looks like the Bat cycle, and I got to sit in it, so that was cool.
Oh.
Yeah, we talked about a lot of interesting, technical things, but actually a lot of personal things. We're at dinner and chatting, and it's fun where these conversations can go.
But you knew who will.i.am is, or like Twilio you didn't necessarily know, but will.i.am. I always got a kick out of it. I thought when you were in New York, you were kind of pushed aside a little bit. Like here, you were like the star person, and then you were suddenly like, pushed aside with Katie, I guess, because I thought you said that the other person with the K for a last name was coming in.
Oh yeah, Kim Kardashian?
Yeah.
Oh yeah, and nobody could really get that close to her. She had this was, I think, right after she had the incident, the physical security
Paris?
incident. And so she had a little entourage. The only person getting close to her that day was Salma Hayek. So
there you go.
She got to get in.
I mean, Annie, do you know any other scientists? I mean, even Jennifer Doudna, who's here, I don't think her life is as glamorous as yours. Do you think it has to do with that you're making stars?
It could be that, yeah. I think there's a lot of interest in, climate change with a lot of really highly influential celebrities, alternate energy sources, and so, the AI boom and how we're going to power that. And so I think that also has something to do with it.
Because this is such new technology, I don't normally ask and I didn't mention this to you, and you can tell me if you can't answer it, but I'm just wondering how politics are impacting what you all are doing, or government funding. I don't know, maybe I'm not phrasing the question quite right, but we see a lot of resources being taken away, and certainly with everything that's going on, we're talking about energy a lot. How does that impact you all?
So thankfully, we haven't been negatively impacted by the new administration. It would be nice if it was a higher level of funding to develop key technologies at universities and in the laboratories. The NIF itself isn't negatively impacted because it's funded by NNSA, which hasn't taken a hit.
Yeah.
And then, of course, the private sector is still going at full force in the fusion space. We have seen an increase in funding in certain areas, but not as much as we had hoped. And so the government is trying to support fusion energy, but not at the pace that it needs.
With Artemis going around the moon, I know you talk about rocket energy a little bit, but does that have any positive impact on you all?
So I think just the general excitement around new cool technologies and fusion is one of them. So when I was at the Mars conference, somebody talked about putting a fusion reactor on a rocket ship and flying that to Mars. Yeah. I don't agree that that's going to work, but it's great to get the fusion excitement out there.
So why do you know already that might not work? What would the challenge be about that?
I think the particular approach, so it's the particular approach that would work for that is really difficult to get going in terms of this hot, dense plasma to the right conditions to make fusion. And I also think that you don't want to be anywhere physically near a nuclear power plant. And so if you're on a spaceship and you're right next to a nuclear source, that it could be a personnel issue.
I know
it would kill you, but yeah.
But maybe not in the short run, right? Doesn't it take a little while?
Yeah, we don't need to get into the details here, but the scheme that was being discussed was a little bit out there.
All right. Yeah. Well, what are some other out there ideas that you think might be doable? I imagine you heard some phenomenal things.
Yeah, the robotics was really, really cool. Space travel in general, getting farther, growing things on these planets. I heard a lot about, I also heard about some cool offshoot technologies like 3D printing a human heart. That was amazing. I almost cried during that one.
Who's working on that now?
Oh, you're going to catch me off guard here because I don't remember the name of the person. But
I thought there was a company called, this was 7 years ago, Cambria or something like Cambrian? No, I
Could
can't.
have been that one.
But they're not in business anymore. But I just was
Oh,
wondering.
okay, not that
But
one.
but to be able to do that,
Yeah.
I think there are companies in LA that are working on that too. So
Yeah.
if you, if something had happened, and the technology had not worked, even though you were driven on it, how might you have pivoted?
That's a really good question. I usually go at something until it works. Like
Yeah.
my husband says, my biggest tool in my toolbox is my hammer, and I hammer it in.
Yeah.
I think we learned a lot of really interesting physics, and so the shift would have been towards, okay, if it doesn't work on this facility, then what do we need to make it work for the next facility?
Okay.
And that's the space we're in now, but the question isn't what do we need to get it to work? It's how big does the next facility have to be to achieve our next goal?
You have an incredible way of looking at things. And I assume that now with Inertia, you're also responsible for hiring people. When you're looking for people to work with you, what do you look for?
I think we're looking for builders, people that are self-motivated, excited, passionate, smart, obviously.
How do you think somebody communicates passion?
I think it's like, and it's hard to pick up in one or two conversations, but you can kind of tell about the way that people talk about their past work when they're giving a seminar. We usually ask about how they would tackle a certain question, and the way they talk about that, the way they think about that question, usually several different conversations. And so, standard list of questions to sort of figure out where their mind space is. And through that, you can kind of tell.
If you could go back and tell your 20-year-old self something, I have this odd feeling that you were like fully baked already at 20. I mean, it's kind of amazing when I think about what you've been doing, what you've been focused on. But if you could tell your 20-year-old self something, what would you tell your 20-year-old self?
Probably to relax just a little bit more.
What does that mean?
Not to worry so much, although I do think worry and excitement drives people. Yeah, I just, worrying that things are going to work out. But again, that's like partly what drives you. I think I could have maybe had a little bit more enjoyment.
We have a class called Resilience, and some of the students here in it, and we have Dr. Sood, who's a neuroscientist from the Mayo Clinic, and he talks about scheduled worry time.
Yeah.
Have you ever
great.
tried that?
I've heard of it, and I've attempted it once or twice, but I do need to try that a little bit more.
It is so fascinating to hear what's happening and what's new, and how suddenly, where things were taking so long, it's really taking off and it's accelerating faster and faster. So
Yeah.
I feel like 2 years shouldn't pass, but like maybe in 6 months to see what's next. What would be a big next step for you all at Inertia?
Yeah, so we're in this first year is really our design and prototyping phase is next, where we're actually going and building out the unit cell laser. So all those purple boxes that you saw, we're making one of those. We're basically nailing all the last technical issues and bringing it to highest TRL. We're also going to be building a target fabrication laboratory showing the key processes. And so the next kind of year or 3 years, if we can hit some of these technical milestones that really prove that we can build this thing at cost, those will be the big next steps. I didn't see what that was.
Oh, technical glitch.
Was that an animal?
Not a big technical glitch, just a small
Cool.
little star.
Cool.
So far in our series this semester, we've talked about next level innovation, and we've heard from people who are working at companies like Meta, or have worked or starting and doing an EV pickup truck at Tello, or working at Microsoft, or doing something with Prellis, which is working on biotech. Or even having a different perspective like Zach Cass, who's written this book and who is at OpenAI, you've heard of, and what he thinks is happening with the future of AI. And we've had a speaker talk about how we can focus on ourselves, what we should do in this age of AI. Hearing what you're doing, that is, it isn't a little, it's in a way mind-blowing, but hearing you so practically talk about it is inspirational for me, and I hope also for all of us here. And I know we'll have a bunch of questions. So I just want to thank you for taking this time to do a chat, and then we'll open it up to the students.
Awesome.
So thank you very much. I'm hoping we've talked about a lot of different things, so you don't just have to have a super technical question, but David, go ahead. Claire, I think David. Is that David? Is that you?
Yeah. Thank you. Thank you for speaking and wonderful questions. I was wondering that, do you see the inertia model as more flexible path for private industry because it allows for smaller, more modular, as opposed to the ITER that requires a tokamak? Or do you think that the scale with the larger lasers would also take up that much space?
Yeah, no, it's not going to be as costly and large as the ITER facility, but it's also a very key different technology. So instead of magnetic fusion and confinement, it's inertial. And one of the nice things, and you mentioned agility, one of the nice things about inertial fusion is that you have a driver, but your target and the way that you're creating the fusion is decoupled from your driver. So you can make changes there, you can iterate, you can make it work. Whereas for the ITER, you're sort of building it one time, and if it doesn't work, or if you have to change the geometry or size, you need a new building. So yeah, it is more flexible, definitely, to have inertial confinement fusion.
Understood. And could I ask a quick follow-up?
Yeah.
With the shots, I'm wondering the debris that flies off of them. How do you deal with that?
Yes.
I like to call it dust, stardust. Is that what do you all call it?
I like stardust. We call it debris. He's right. Because we don't want that. So we vaporize the targets, and you actually want to, because otherwise you send a bullet flying through to your other side of your chamber. But you want to be able to dispose of it in a way that it doesn't like goop on top of the laser optics. And so that's a key thing that we're going to be developing and working on and focusing on. And part of that's chamber gas flow and debris cleanup and debris mitigation. And that's a key operational aspect of these facilities that you have to continuously work on over time. And that's one thing that the ITER facility maybe doesn't have as much issue with. So there's pros and cons to both approaches, but that's one of the cons that we actually have to deal with. There was a large program called the LIFE program that was actually existent at the lab back when I started. And they looked at a lot of these key issues, but we're re-looking at them now at Inertia.
Understood. Thank you so much.
Yeah.
Hard to see, yeah.
Over here.
Oh.
Thank you for visiting us today. I have two technical questions. So first
You
one.
guys, do you mind actually just introducing yourself also, just so we know, or what you're studying, or,
Yeah, sure.
or something you want us all to know?
Absolutely. I'm Hagen. I'm a third year. I study engineering science. Okay. And my two technical questions were, so first, I would be interested how you get your tree theorem. So the one part of the fusion equation, because that is not super common, as I assume, as an element. And then the second question would be, how do you inject those small targets and hit them so precisely? Because it's a huge reactor, and I assume there's nothing in the middle there. So how do you get them to the right position and then hit them precisely?
Yeah, and we actually have a lot of key things we're working on. One of the key things we are working on is a target injection and tracking system. We call it Thunderstruck because I think that name is cool.
Not as cool as Stardust, but go ahead.
Yeah, this is another area where the LIFE program had done a lot of work previously, and there's methods like air rifles with buffers that shoot these targets in. I think if you think of a system like ASML, I don't know if you know ASML, or like the LCLS and how fast the many hertz that they hit targets at with high precision, this is a solvable problem, but it is a huge engineering problem. The bigger problem is actually what happens to the target, the conditions of the target, when it enters a chamber that's been heated by the prior experiment. So that's what we're putting a lot of effort into. So you have an explosion that goes off, it heats the debris and the gas around it, and then the next target has to come in and survive those conditions. And so we're spending a lot of time figuring out how to make the target survive being shot in and being shot into this extreme environment. But the actual like shooting a target in and hitting it with a laser system, it's not really that hard of a problem, and it's something that we're still like proving out in the first phase though, before continuing. And then, sorry, your first question was about
tritium.
Oh, the tritium, yeah. So any fusion scheme would require to breed tritium, would need so much tritium that the government's not just going to keep supplying that and can't. So what every fusion scheme is doing is taking the neutrons that are born in those reactions and heating a blanket material that contains lithium, and that makes tritium. And then that also goes to the heat exchanger, and that's how you get your heat out. And so all schemes have some version of a blanket containing lithium, so you can do neutron reactions on the lithium, make tritium, and then capture the tritium and reuse it. And then, but to get going, definitely, this is one of the key areas that the government is going to really have to step up and help with, and they will once there's a viable concept, is supplying enough tritium to get that initial phase up and going that you can then just breed your own tritium.
So just to clarify, so you collect it from the wall where the neutrons hit the wall, basically?
Yeah, there's like it'll be a molten lithium wall that flows down, and then you extract the tritium from that. And that's another, we have a small, this is another key aspect of the LIFE program that was already looked into this. Of course, a lot of the different fusion companies are also looking into this. And there's even some isolated companies that's all they're doing. So we're working with them. We are also doing that as part of our inertia activities, is making sure that there's a self-consistent tritium fueling feedback loop that makes sense.
Thank you.
Yep.
Hi, thank you so much for your talk, and I really appreciate the graphics also. Your team is very impressive. I was wondering, you mentioned that the capsules are made of lead and that it always gets recycled and you get to reuse it, and you have the ability to store it all for up to a year in your facility. What is that process like, and how do you, if it gets vaporized, like how do you recycle it?
Yeah, so the gas in the chamber flows in a specific way to get the debris out of the chamber. And there is a processing step for the lead, which I don't know all the materials details about the reprocessing of that lead, because that's not my specific area, but that is an area that we're looking into. And you can actually store more than a year, but we are processing it continuously to use it again. And it doesn't become radioactive in a way that requires long-term storage. So it's like low-level storage on the facility grounds for an entire year you can store up to. It would be great if we didn't have to use lead. The lead is not the capsule, the lead is the can. The capsule is just carbon. And so the first thing is do the thing we know is going to work, and so that's why we're using the same can and shell and capsule. In the future, we could look into other schemes which get rid of the can. It's just really hard from a physics perspective.
Over here.
Hey.
Well, hello. Thank you for being here. My name is Zach Pastorian. I'm a Haas student here. And I wanted to say I understand. Yeah, thank you. I understand the vision, and it's extremely impressive and revolutionary. And I guess that being said, I just wanted to know, have you considered like the greater long-term risks and mitigants to like expanding, at least like in your vision, like with these power plants? And if so, what are they?
Okay, so you're speaking about potentially proliferation issues, or like the risk, you said risks?
Yes, that's correct. So like as you're expanding, like making more of these power plants nationally or wherever, globally.
Yeah, so there's a lot of our technologies surrounding the laser system and some of the target fabrication that are controlled technologies. And so currently we're keeping them controlled in a way that's consistent within the US with our restrictions. And so one of the risks could be to get that laser technology out to other countries. And I know that the current plan is to protect that information. I personally haven't thought about how we expand that to other countries. But there are people that are not just scientists that are thinking about those types of issues. And then in terms of the tritium, there's very strict control methods for controlling the tritium, so that's not extracted. And we wouldn't have enough anyways in any given one day at the plant to be of issue, because you want to keep your tritium in your system low enough that it doesn't pose a hazard risk. And so part of our key tritium and fuel recycling system has to keep the tritium below a certain level, and that's a fraction of a kilogram. And for that doesn't pose a significant proliferation risk. So those are the kinds of things that would be of issue. Otherwise, just making sure that there's, you control the population surrounding your plant.
Why, and perhaps I'm being dense, but what would the issue be if this would go outside the U.S.?
So there's some key laser technology that you want to keep controlled, because some lasers are also used for defense.
Oh, thank you.
Yep.
I'm curious about how the transition from being in the lab doing the science to going to being an entrepreneur and what your day-to-day work is like. And specifically, like, are you still on the floor doing the hard science, or are you purely kind of doing it from a management position? Yeah.
That's a great question. So I'm chief scientist at Inertia, and I'm happily having Jeff be the CEO. So I do business things when he asks me to, but I'm not in charge of the entire business at Inertia, which is great because I'm not that major. So I'm still doing the hard science at Inertia. I'm managing though, but I love to get into the details. So whenever I can or have the excuse to, I'll dive down into the details there. Still doing the basic science at the lab and managing as well, but bringing in the right people at Inertia. Going to Jeff to talk with investors when we need to, going to talk to the government, that kind of stuff. But I'm not, I don't need to do all the business things. Yeah.
Very cool.
Yeah.
Hello, I'm Levin. I'm a bioengineering student, third year. My question is two technical questions. The first one is, why would you need such a large system? Because the more light travels, the more attenuation you would have, and the more sort of light diffraction you would have. That's part one. Part two, do we have a better method of extracting the energy than just steam engines?
Yeah, it's the oldest method. Just boiling water is the oldest method. First, I'll answer that question, which is we are looking into a high temperature heat market. So just using the high temperature for things like, I think it's like the concrete high temperature heat market, where you don't have to convert it to electricity through that method. But no, that's the simplest method. I think we're going for not developing everything new from the ground up. And it's sort of like a really well-known process and way to convert to, the steam turbines.
So is that when you're seeing that come out? Can you see it in the...
That's from are you talking about like from a coal plant?
Yes, I am.
That's the other. And then, sorry, I forgot the first part of your question.
The light attenuation. When you have
Oh, yes. So the reason, so there's a few different pieces to this. So you want to make the laser energy higher, bigger. And that is different from just making the chamber bigger. And you want to do both. So you want to make the energy of the laser increase so you can drive more fuel mass. And that's how you really confine and burn up the fuel, and you want to get more fuel in to burn. So that's how you get your fusion energy output to increase so much. Does that make sense, or do you want me to try again with that? So
It's
yes.
just my idea. If you're shooting a laser,
Yes.
laser would be strongest the moment it comes out of the sort of the machinery, I guess. The
Yeah.
more it travels, the more attenuation would have.
Right.
It would diffract more.
And the second part of that was the chamber size, and why is the chamber so big? And it's because like when you have basically a miniature bomb going off, you want your laser system to be as far back as you possibly can. But the thing that limits that is things that you brought up, not just like the attenuation going through the gas of the laser, but also like what we call the F number of the laser. So you have a certain optic size and you have a certain distance that it travels, and the way that that hits the target can change the physics that's going on in the target. And so it is a constant trade-off between, for the chamber size, for a lot of different, those are two of the things. Another one of the things is this fuel conversion blanket. You have to put it in there and get it as close to the neutrons as you can.
And lastly, is there a specific frequency for the laser?
Yeah, for our laser, we're using 351 nanometers.
Now we'll have to kill you.
Same as what we're using at the NIF. The reason for that, and we frequency convert it down, is because it's more favorable for the target physics.
Thank you.
Yeah, hi. I was wondering, what is the expected lifespan of one of the nuclear reactor, and how do you manage with maintenance?
Again, one of the things, luckily, and I forgot to mention, our third co-founder actually ran the LIFE program. So when we started off this endeavor, I said, you know, I want somebody that's already thought about all these issues at least once and now knows what to look into next. So the facility is meant to be a normal 30, 40 years facility, but it's going to require continual maintenance in all the different pieces of the system, and that includes the chamber, the optics, everything. And so there's a lot of ideas of how to do this with robots and how to engineer the system to do this, but we're also working with a large, and we're looking into different large engineering firms that have already done this and know how to do this. And I won't say the name of the firm that we're looking into working with, but this is a very serious and detailed problem, and something that we're, again, it's like a back and forth, because I want to stick as much laser energy and laser glass in every possible nook and cranny as I can to get the most into our system at a specific angle. But then you can't get your robots in there to change out the optics. And so it is a continual back and forth for these types of issues. And then for like any given component, it has a different lifetime. Some of them are 3 years. Some of them are a couple of months if they're disposable.
Hi, my name is Agustin. I'm an exchange student from Chile. I wanted to ask you a question because I've read some things about. This is not my area of expertise, but as we know, as you explained, we have like high energy neutrons from the fusion reactor, like constantly, like bombard and degrade the reactor's materials. Regarding the commercial viability that you also talked about, what is our best solution right now to protect the first wall over the long term?
Yeah, it's a great question. We are looking, actually we're working with a team here in the nuclear engineering department at UC Berkeley, and they're looking at different materials and survival of those materials over time. The way that so there's like the distance, right, the larger size. We also have xenon gas in our chamber to help protect the first wall. We have a certain amount of heating we accept at the wall, given all of these things. These are miniature stars. I mean, it's a lot of power and energy, but they're tiny in a massive chamber. So the size of the chamber and the xenon gas inside are really, really key. And then you have materials that are more radiation resistant, and these newer materials of ferritic steel, for example. But then they also need to be replaced and refurbished over time. There are also other ideas like a completely liquid first wall that never damages. We are looking into that also. That has other issues for the physics of the system. So there's trade-offs.
Thank you. I wanted to ask you like just a short second question. Do you also work with, you only work here like in the US, or you also work like in Europe with the ITER, I think it's called, that's like public also?
So we have collaborators that are international, and we're looking at doing some small scale experiments at laser facilities in France, for example. We are doing a lot here because that's where we're based, but yes, no, we are doing those types of experiments where it makes sense. So for example, one of the easy things we can test in a small-scale laser facility is heating the xenon gas to the right conditions that the conditions decay to, which aren't that extreme, and then looking at laser propagation through it. And so that's one thing that we're discussing, working with a team in France on.
Thank you.
Yep.
Hello, yeah, my name is Mahesh. I'm a second year studying data science here. I'm over here.
Okay, thank you. It's like amazing how hard it is to see up here.
Yeah. My question revolved around like the dynamic of the team. From my limited understanding, so like Jeff's background is more on like the software, computer science based stuff, not physics. So how did you go about like forming this team and making sure that like everyone could contribute in a meaningful way to the final mission of Inertia?
Yeah, I was super excited about how our team came together because basically now you have the person that ran the LIFE program, Mike Dunn. So he knows how to take the fusion energy and convert that to electricity. He's also a physicist. And then I worked on the fusion result and know that in really a lot of detail. And then Jeff knows how to build a company and has a lot of connections, and really, you know, that is not to be understated. A lot of scientists have tried to build these companies by themselves and don't know how to run a major company. That being said, I think I met with Jeff for probably a year or some large fraction of a year. Every week, maybe multiple times a week, you know, he would send me physics questions. Have you thought about this? Have you thought about that? Brilliant guy, brilliant person, and you know, caught on really fast to the science and asked really good questions. Has good ideas even. So I think our team works really well together on their own individual pieces, but can like cross over and ask good questions to the other people.
So you would say like he learned more about like the technical background while picking up this role rather than having like a strong background beforehand?
Yeah, actually, so when we first met, it was many months before we decided to start the company. So in that time frame of those many months, he learned the physics.
Why do you think, after having so much success with Twilio, what was it about the prospect of being able to work with you that was so fascinating?
Oh, he just loves scientists. He's sick of those computer scientist people. He just loves a physicist. Now he can't, you know, he regrets that decision. He thought the science was cool. He really wanted, you know, he was interested in the mission. He didn't want to just start another software company. Kind of been there, done that. And he said, you know, he would say in the beginning, this is what I want to do for the rest of my career, because he just thought it was really cool and wanted to build a big laser, I guess.
As one would.
Yeah.
I like it when you talk about building a star.
Yeah.
It's pretty incredible.
And stardust. I'm going to use that now, too. It's not debris. It's stardust.
Annie, oh, yeah.
Hey. My name is Alex. I study here.
Yeah, hi.
CS, so it's quite refreshing to see like a talk that's not just AI, but like more like hard tech, hard science. Even though I do study CS, so my question would be, like, how does your day-to-day look like? And like, I often hear like more from the software side, like that a lot of like workflows have been enhanced, so to say, by AI. So I'm wondering, is that something that at all pivoted into how you work or what you're working on? Or would you say, okay, it hasn't really touched or changed much in your field?
I think it already has started to, you know, help accelerate our progress in searching for design modifications. I think it has a lot of impact to really, you know, boom, accelerate soon. I've been using it to tackle smaller problems, not to completely design an entire new system. I think it's hard for AI to kind of design or extrapolate into a space that's never been. But if you're trying to optimize around a space you know pretty well and you can really bound the situation, you can significantly accelerate your progress. So using it a lot to kind of, one example is exactly how you define the laser power versus time. We have to tailor these pulses at the sub-billionths of a nanosecond, sub-billionths of a second or nanosecond level. We need to shape the laser pulse as a function of time. And there's pieces of that system that we can optimize now with AI, whereas before you'd be doing it like one simulation at a time by hand. So really seeing that come together. Also just like company building, all that kind of stuff is really helping pulling all of the plans together. But in terms of the tech, yeah, it's helping us design and analyze the data faster than we could just by hand. But so far, we haven't quite seen the huge payoffs that we can get when we finally teach it to design a completely new system.
Thank you very much.
Yep.
I know people will have questions for you one-on-one, but you are so patient with answering questions across the board, whether it's deeply technical, which I definitely don't understand, to less technical. I am curious, is there a question, I mean, you get questions all the time. Is there a type of question that you hate getting, and what is it?
Oh. You caught me off guard with that one.
Thank goodness.
I hate getting... I think students that ask questions are brave, and I don't think there's any bad question there. I did have, so in this conference where I met Jeff, I had a celebrity ask me if I was going to blow up the world, and this was like right after Oppenheimer came out. So, but I didn't hate that question. It was just.
Was that a serious question?
It was, yeah, it was.
Are you going to tell us who that
No,
celebrity was?
I bet I shouldn't. No.
Are you,
I think you're recording this, so I'm not going to.
We can edit. Sorry. No hint, though? Male?
You're
No. All right. We really don't want to know. But so what did you what was your answer? Are you going to blow up the world?
It was like, no, we'll just turn the laser off.
Just turn the laser off.
It's really hard to get these tiny plasmas to these right conditions. So I think the picture in some people's minds is we're actually creating a nuclear explosion, but we are on a tiny, tiny scale. But yeah, it's quite different.
It's not always that we can have a conversation about something that is so truly cutting edge in a way that is also practical, that maybe all of us could at least say one or two articulate things about from listening to you when we are next at cocktails or dinner or playing soccer with friends. So thank you so much for your time. I know you'll stay behind a little bit as students have extra questions, and thank you.
Cool. Thank you so much.